guys, let's dig into how this actually works. The microcontroller that I'm using is an Arduino. Most of the pins of the Arduino are sent over to a motor driver seen in the middle. This motor driver is an L293D, and it is used to control the PWM signal from the Arduino to the motors. The motors themselves are powered by 5 volts from the wall outlet. There is also an LED in the system that lets the user know when the balance beam is within 2 degrees from horizontal. The angle calculation itself is done by an MPU 6050 that measures gravity based on the angle. Okay, so let's take a closer look at the wiring. Pins from the Arduino that are used for the motors are 9 through 11, 2, 3, and 5. These pins are connected to the motor driver, and if we look closely, for like pins 2 and 3, those are connected here and here respectively. These are used to control the motor direction or polarity of the DC motor, not actually what transfers the power or the PWM signal. The PWM signal comes from this, is what corresponds to this pin right here, and if we trace it back, it goes to pin 5. Now it's important that there are only specific pins on the Arduino that can be used to transfer the PWM signal, and they're denoted by this little squiggly sign. So 3, 5, 6, 9, 10, and 11 can be used to transfer that PWM signal. And so as long as you use one of those, which I did, I used 5 for this motor, then you should be good. Now for the other side, I used pin 9. You follow the blue wire, the motor driver is kind of flipped on which side is which. You can find a data sheet for this L293D and it'll tell you what pins are what. But yeah, that's most of what the pins are going over to the motor driver used for polarity and PWM signal. So this side is for one motor and this side is for another motor. It's important to note that the power for the motors does not come from the Arduino, but rather from an external power supply. Of course, it's not a 9-volt battery plugged directly into the breadboard, but this is just used to symbolize that it's coming from an external power supply and not from the Arduino. Lastly, there is the LED that has a connection to pin 7, and of course it has a pull-down resistor in series so that the light bulb doesn't burn out. And this, of course, was just used to let the user know when the beam was balanced. But yeah, that's all the wiring for this project. Okay, so let's look at the code. So for this code, there are several things that are important to point out. First off, we have the PID library that I use. This PID library can be easily added by going into the sketch, include library, manage libraries, and this is the one that I use, this one by Brett. It worked well. And that's how you include it. You just click this button right here to install. Of course, mine already has been installed, so the button's not there, it says remove, but that's all you have to do, and then the library is added. So once you have the PID, you also need this Adafruit MPU 60 library, and that can also be found in similar fashion. So some of the major points of the code is right here. This is the tuning gains that we have done. This is KP for proportional gain, KI for integral gain, and KD for derivative gain. And these have all been tuned to precisely reflect a response from the system that I want. Here is the PID statement. This is the initialization for the input, which is the angle, the output, the set point, which for me is 0 degrees or horizontal, the 3 different gains, and this, I'm not exactly sure what it does, but you have to say correct. Here are the pins that I use for my motor drivers and the light bulb pin. This here is the setup that is used for the code. This block of code right here is used for the MPU 6050 setup. This is all found in the library, again for this code as well. Down here, this is the set point that I mentioned earlier about for the PID controller, and we want it to be 0 degrees. This is all also for tuning and setting up the PID controller with output bounds between -200 and 200 so that the PID controller itself doesn't try to make a too high of a PWM signal to the motors. And here this is just the motor pin setup, the light bulb setup, and then wait 4 seconds until we start the actual loop. So for the actual loop here, the first line of code that we have just sets up the actual values that the MPU 6050 is reading, the first being acceleration, and then angular rate rather. This is like for a gyroscopic motion. Of course, we didn't use this. And then this is also temperature, which I also didn't use that. So the only really thing I needed here was the acceleration. So the acceleration X is printed out here, and the rotation as well, the gyroscopic motions. in radians per second, and this was in meters per second squared. This is the major line of code. This is actually how we measure the angle for our balance beam. What we do is we take the acceleration in the y direction and divide it by the acceleration in the z direction and take the arc tangent between them. So that will give us the angle in radians. We need to convert it to degrees here. And then this number is just to correct for a bias error that I noticed in the MPU 6050, so that it is actually 0 degrees or horizontal whenever it is supposed to be 0 degrees. This is just corrected for bias error again. Here, this is where the PID controller takes the input and computes the output. Here is the base for the two different motors. The reason they're different values is because one motor was stronger than the other. And so they have to have different starting PMW signals that represent the starting RPM. Now for here, this is where we actually change the RPM. We start with our base RPM, and then we add what the output should be from the PID controller. And then we bound it between 0 and 255 because the range of values for a PWM signal is between 0 and 255. 0 being 0 volts and 255 being 5 volts. Here we just output the angle and the output just so you can see what's going on in live time. And then here, of course, this is the if statement that tells us if the angle is within an absolute value of 2 degrees, so pretty close to horizontal, then we turn on the light bulb so that the user knows that the beam is balanced. And here, this is actually how we control the motor. Don't worry about the commented out sections, but if the angle was tilted onto one side, then we only wanted one motor to turn on, and if it was tilted onto the other side, we wanted the other motor to turn on. And this is just what's going on here. So we're saying turn this motor on if the angle is less than 0, and then turn the other motor on if the angle is greater than 0. Yeah, and that's all the code there is to this. So I wanted to give you all a little bit more of an overview on how the PID controller works for my system, because it can be kind of hard to understand. So the first part of the PID controller is the proportional gain, denoted as KP, and pretty much it can be thought of as how fast the system responds to the error. So like for my system, if the error was the angle, right, how far away it was away from 0 from horizontal. And so increasing the KP means how fast the system will respond, meaning the motor speed will increase based off of how far the balance beam is away from 0. And yeah, so a higher KP will mean that a higher angle will have a greater effect, and a lower KP means that the same angle will have a lower effect on the system. And again, for this project, increasing KP just meant that the angle had a greater effect on the motor speed. The second part of the PID controller is the integral gain, denoted by Ki. This corrects the steady state error and kind of adds like a time element into the system, if you will. So without it, the steady state error could be anywhere. It could be off. It means that my beam might not go to balanced without the integral part of the PID controller. So pretty much it just fixes the error of the system over time. And for my project, just means that it will bring it to horizontal over time. Also, a benefit of having an integral part of the controller is that if the beam is taking a long time to get to 0, to get to horizontal, I mean, that means that the controller will increase the motor speed so that it pushes it up to horizontal, whether it's, if the beam is stuck or if it's just taking a long time to reach stability. If you increase the Ki, it will just increase the motor speed so that it gets to horizontal quicker. And the last part of the PID controller is the derivative gain, denoted by KT, and it decreases overshoot and oscillations. So if you remember from the KP graph, if you increase the KP, that means you'll have higher oscillation and higher overshoot. So if you had a KD, that KD part will kind of offset the negative effects of the KP, of the proportional part, meaning that it will lower the overshoot of your system and have it have less oscillations and be more stable. So for this project, increasing the KD meant decreasing the motor speed when the balance beam is getting close to horizontal, so that it didn't overshoot and then tilt back far in the other direction and get in this very unstable kind of seesaw action. So that's like the main three parts of the PID controller and kind of what they look like in my system.